Hello. As you may already know, the world we are living in is constantly changing. New technologies and scientific breakthroughs are being created and are advancing our society at an astronomical rate. To keep up and adapt to the state-of-the-art technologies, Michigan State University has proposed the need for a new interdisciplinary science, technology, engineering, and mathematics institution. This building will house new classrooms and laboratories for faculty and students to further advance the future of STEM learning. This presentation will cover the preliminary design for MSU's new STEM facility project called the Shaw Lane Reconstruction and Shaw Power Plant Renovation, designed and presented by our team, the Spartan Builders, as part of the Fall 2020 Civil Engineering 495 Senior Design course. In today's presentation, we will be introducing our design team, the project overview, our design team coordination, and each of the 5 disciplines will present their preliminary design. After that, I will be covering the project construction schedule and cost, and finally, the closing remarks. First, let me introduce you to our team, the Spartan Builders. We are a group of senior civil engineering 495 students comprised of 6 different disciplines and 7 members in total. My name is Alexis Lee, and I am the project manager of the group. Other than that, for disciplines, we have Robert Caldwell for structures, Ryan Isley for hydrology, Yuru Bao for environmental, Sam Malatesta for environmental, Noah Drosty for pavements, and Josh Myers for transportation. Our design team members are involved in groups such as the American Society of Civil Engineers and Environmental Engineering Student Society. In addition to this, our team has had multiple semesters of professional internship experiences. Based on our prior knowledge, along with the guidance of MSU faculty, we have prepared a preliminary design for the Shaw Lane project. The Shaw Lane project principal requirements provided to us are as follows: to design a new building to be architecturally compatible with the best features of the existing Shaw Lane power plant building, to develop a building design to be harmonious with their surroundings, to minimize negative water quality impacts of the Red Cedar River watershed, to provide transportation options that maximize and prioritize pedestrians while minimizing movement of vehicles, and lastly, to preserve and protect existing natural areas while providing efficient land use. Based on the project principles described in the previous slide, the Spartan Builders team was asked to provide the preliminary design for these aspects: to design key structural elements for the primary building, to develop a multimodal circulation plan and road and intersection geometry, to design paved surfaces for the site, to design stormwater collection and treatment systems consistent with green practices, and to ensure all state, local, and federal rules and regulations are met. Before the start of the project, we developed and committed to a team contract. The team contract outlined many guidelines such as making project commitments, participation, communication, decision-making, conflict resolution, and meeting protocols. All members had to read and sign the contract before starting the project. Also included in our team contract was a link to our project share drive due to the virtual nature of our meetings. During the project, we agreed to have weekly full group meetings via Zoom. In these weekly full group meetings, we resolved design conflicts and restraints. For example, it was very prevalent early on that many of these designs had design interdependencies, such as pavement specialists needing to know the transportation design layout before making cross sections. Because of how often our team met and how comfortable we got with each other, we were able to iron out any design conflicts through group texts, email chains, and smaller group sessions if needed. We committed to design progress each week. The project manager set a schedule for each discipline that outlined a certain percentage of design progress each week of the semester during the first 2 weeks of class to pace the different disciplines as needed. It was mandatory for each discipline to share what they had completed each week during the start of the weekly meetings to ensure progress was being made. Based on how information heavy our weekly meetings were, meeting agendas and meeting minutes were created and noted action items for each members for the following week. During this time, we brainstormed ideas, recommendations, and tasks for each other, if needed, based on what was talked about at the design meeting. And lastly, any unresolved design issues were immediately brought up to a faculty member via project manager.
I will introduce to you now the transportation segment of our design project. I am Joshua Myers, the design specialist for transportation. Michigan State University, being the client, would like to introduce more bicycle and pedestrian pathways on campus. They also would like to preserve existing natural areas while providing a roadway design with efficient land use. The project vicinity is shown to the left with the new proposed STEM building being that of northwest of our current intersection of Shaw Lane and Red Cedar and southeast of Spartan Stadium there. The goal of this project is to convert North Shaw Lane into said pathways for bicyclists and pedestrians and to utilize South Shaw Lane for all bounds of traffic. It currently serves as the eastbound carrier for traffic, as North Shaw Lane serves as westbound. The new project would intend for all of the traffic to be traveling on South Shaw Lane as eastbound two-way roadway. The design considerations for the intersection are Capital Area Transportation Agency's buses, also known as CATA buses. Students are very familiar with them, but they have a turning radius that we need to consider for. We also would like to consider pedestrian safety due to the campus's high foot traffic volumes. The first step in redesigning the intersection of Shaw Lane and Red Cedar was to do a traffic analysis to make sure that our new geometric design would in fact work and maintain traffic, if not improve it. We were given data from Michigan State University, which included the present turn volumes for the intersection of both bounds of Shaw Lane as they intersect with Red Cedar Road. The present volume of traffic was used in a simulation of the proposed intersection design using software called Synchro 6. This software can be seen in figures 1 and 2, figure 1 being the timing window for turning movements, as well as giving us an optimized phase length. You can see for the first two columns, being that of the roadways, that those are east and westbound, giving a 26-second green light, and then to the right of that, north and southbound Red Cedar, giving 16-second green light. And to the right of this image, you see figure 2, which is the geometric. It's a rough geometric, as to the software doesn't really care about alignment and how everything physically will look. It's just that the turning movements are in the right place. So to use this software, the obtained data for present traffic volumes were projected out to 20 years at 1.5% growth rate using an equation provided by MDOT, and that is tabulated below those two figures in table 1, and those numbers were in fact used in Synchro to get the level of service for our proposed geometric design, which was level of service A for both peaks in the AM and the PM, as well as the light timing for the phase lengths. In this image here, you can see the current layout of the intersections of South Shaw and North Shaw as they cross Red Cedar Road. The current layout features a large splitter island between North and South Shaw Lanes, as well as to the west of Red Cedar Road. It is proposed that this space be utilized, as well as eliminating the area of North Shaw Lane to the north of the splitter island for more green space, and then redesign the pedestrian sidewalk in that area. All of North Shaw Lane to the east of Red Cedar will be repurposed for the bicycle and pedestrian pathways that are proposed and desired by MSU. All sidewalk ramps to the new roadway will need to meet the Americans with Disabilities Act, commonly referred to as ADA, of a no more than 2% incline. And all of those ramps, inclines, will need to have detectable warning devices. For the proposed layout of the new intersection, South Shaw Lane is proposed to be widened, and these are from the current edge of pavements, 12 feet from the south edge of pavement and 24 feet north from the north edge of pavement. These are to accommodate the new turn lanes as well as the travel lanes that will exist throughout the roadway. In the northwest quadrant, a slip ramp for right turning the south to westbound traffic is proposed. The main consideration for implementing something like this is the CATA buses to make that right turn radius. Before, they had just a straight through as westbound was currently on North Shaw Lane, but for this case, this close acute angle was too tough for them to make that turn. We projected using microstation turning software, so a turn ramp or a slip ramp there was deemed appropriate. The north to eastbound right turn lane on Red Cedar did not require a radius redesign. Other than that, it will be moved 12 feet to the south to match in with the new edge of pavement, but buses already make this turn and it is not deemed too tough for them. Other than that, Red Cedar will just have pavement marking layouts as shown, and east and westbound will be 5 lanes, one for a designated left turn lane, and then a shared through and right turn lane, and then a designated through lane. 2 reception lanes on either side of that intersection. A lot of parking lot 39, which is shown to the northeast, will have to be removed as we do not want to get too close to the engineering building, and it was chosen to go that 24 feet north instead of to the south. As I wrap up the transportation design segment, I would like to leave you with some limitations and recommendations due to the scope of this project. As I mentioned before, the parking will be impeded upon as parking lot spaces will be taken away from lot 39 to the north, but also the exit ramp or the exit lane rather would exit out into North Shaw Lane, but since North Shaw Lane will be repurposed as walking and bike paths, this will now become obsolete and they will need a new area to exit from the parking lot. It is recommended that they exit with a shared driveway perhaps into and out of the parking lot on South Shaw Lane or even to the west out onto Red Cedar, but that is not as recommended because of its proximity to the intersection, and we wouldn't want the turning of the cars out of that parking lot to impede that intersection. Also, the Farm Lane intersection, which is to the east of this intersection, you can see it on the graphic to the right. It's that north-south road on the very edge, right edge of that image. The widened road will cause that intersection to be redesigned as there will be more lanes, both bounds of traffic, the turning movements will be different. We recommend similar treatment to this intersection be done as redesign, traffic analysis, and also pedestrian safety for that. But for pedestrian safety between the two intersections, there will be a new widened road, 48 feet, 4 lanes, possibly more, if there's tapers for the turn lanes, etc. We recommend pedestrian refuge islands anywhere between those two intersections that it is expected that professors, students, visitors will be crossing from the parking lots into the engineering building or Anthony Hall. Thank you very much, and that wraps up the transportation segment.
Hello, my name is Noah Drusty, and I am the pavements engineer for Spartan Builders. To start out, I'd like to give a little bit of a background information on the project as it pertains to pavements, and then also what my responsibilities are. So, South Shaw Lane will be widened as a part of this project, 12 feet to the south and 24 to the north, to accommodate the new lanes for a shared east-west bound roadway. Red Cedar has not been widened, but there has been an addition of a extended or a separated, rather, right-hand turn lane. As the pavement engineer, I am responsible for surveying the existing site conditions, designing 4 pavement cross-section alternates, performing life cycle cost analysis on each of these alternates, and then finally selecting the most cost-effective alternate. So first, I calculated the easels for Red Cedar and for Shaw Lane. These are 20-year easels based on ADT data that was provided by the transportation engineer. This is important because we want our cross-section design to last for its 20-year lifespan. As you can see on the left-hand side, those are all the variables that were used in my easel calculations. Truck factors were given or used MDOT truck factors. On the right-hand side, you can see the documented pavement condition. This is Shaw Lane. There's definitely some distresses and some cracking going on. It's in need of some rehabilitation. So the 4 alternates were 2 full reconstructions or new constructions, and then 2 more rehabilitation style options. There was a full flexible reconstruction, a full rigid construction, and a mill and fill, and then an asphalt overlay. Layer coefficients, as shown in the picture on the left, were determined from the existing site conditions. I compared the site conditions to the AASHTO 93 tables to determine layer coefficients based on how damaged the roadways were. These values were used for the calculations in determining the cross sections of the 4 alternates using a online software called PaveX. You can see just a short example of some of these calculations in these images. Next step was to perform life cycle cost analysis. This was done in a per lane, per mile format. I did utilize some MDOT rates for my different pay items to get a rough idea of the initial cost of the construction, and then this was extrapolated into a per mile, per lane, per mile format. This was then utilized in tandem with the MDOT average rates for follow-up rehabilitations, maintaining a traffic costs, and then user costs to essentially summarize how much the pavement would cost over its entire lifespan. This is good because it's not just the initial construction cost, it looks at it as a whole in its entirety. This is a great tool, but it is not the end-all be-all. There are other important factors related to feasibility and practicality that are important to consider. So once LCCA analysis was performed, we then determined that the most cost-effective option was an asphalt overlay. However, this option is not really feasible. If you think about it in just a general engineering sense, if you raise the roadway, you're going to have to raise the concrete curb and gutter surrounding the roadway. You're also going to have to taper down the new higher pavement to the existing pavement that butts up around the edges of the project. Also, it could have drainage effects, and it's just not really feasible for construction. So where new pavement where existing pavement is a mill and fill will be utilized. This mills down the existing pavement and repaves over top, matching the existing grade. Where new pavement needs to be constructed due to alignment changes, a flexible pavement structure will be utilized, a new flexible pavement. As you can see, there is a cross section for construction for a proposed 4-lane section that will be utilized on Red Cedar, and a proposed 5-lane with variable turn lane cross section for Shaw Lane. Moving forward, I estimated the capital cost of the construction. This was, again, utilizing MDOT bid prices. I used MicroStation to summarize my existing area and my new pavement area, and then I used Excel to summarize the quantities of the pay items. Many codes and regulations were considered during the design of the pavements for this project. Both Michigan Department of Transportation and Ingham County Road Commission standards were considered during the pavement design. Some important specifications were specifications on cross slope, PG grade, and minimum thickness for flexible and concrete pavement sections. Permits are also required for lane closures and detours that are needed for construction, and also for right-of-way permits are typically required from the governing body or owning entity of the roadway. While these permits are all important, it is typically the contractor's responsibility to acquire them, and Spartan Builders will delegate the responsibility to the contractor. Last, but definitely not least, some sustainability considerations. The main sustainability consideration is to utilize 30% reclaimed asphalt pavement in our base or leveling course and 15% reclaimed asphalt pavement in our top or wearing course. Some additional considerations that will not be used for this project would be to add a rubber modified asphalt. This provides good performance on bigger projects, but is not as competitive on smaller projects. Our project is a little bit smaller in terms of area, and it wouldn't really be feasible. Mill and fill, recycle in place is also not applicable for similar reasons. And then finally, the use of a recycled aggregate base or crushed concrete was considered, but Spartan Builders has elected not to pursue this option because of a professional recommendation. This concludes the pavements portion of our project. Thank you for your time.
Hello, this is Robert Caldwell, covering the structural design section of this presentation. Sections that are going to be covered are the site layout, the architectural layout, the structural layout, the loads and loads combinations, structural analysis, design of individual members, and a summary. The image on the left shows the current location of the Shaw Lane Power Plant building, and the important considerations for the location of the new structure are going to be environmental impacts such as removing trees currently on the site, and also the addition or removal of paved surfaces. Also, the location of underground utilities that may need to be worked around also has to be considered in the position of the new structure. Design requirements that would affect the site layout of the new construction would be that the building is required to be an L shape broken up into two main structures, with the first being 80 feet by 160 feet and the second structure being 80 feet by 200 feet. This would make the best location to attach the new construction to the current Shaw Lane Power Plant building on the east side of the building, with the 160-foot section attaching to that east wall and the 200-foot section being wrapped around the south side of the building, connected by a small corridor. This location would avoid an underground steam tunnel on the far left side of this image shown on the pink line, and it also will not require the additional removal of any trees on the site. This location would require the removal of parking lot 79E, but this would aid in the removal of paved surfaces on the site. The structural and architectural design of the building should work together to help support the function of the building. The design requirements that will impact the structural and architectural layout of the building are that it must be a 4-story building including a basement level, and the height of the building must be at least 55 feet above the ground, but also must not exceed 65 feet. To help in the structural design of this building, The structure will employ symmetry across all sides of the building to aid in future structural design for both buildings that are to be designed. The 160-foot section and the 200-foot section will be made structurally similar to each other such that only one structural frame will have to be designed and analyzed. The figure on the right side of the screen shows the proposed framework along the north-south view of the 160-foot section of the building. It shows that the building will have a 15-foot basement level, a 15-foot first floor, a 12-foot second floor, a 12-foot third floor, a 12-foot fourth floor, as well as a 10-foot roof. This will put the height of the building at 61 feet above the ground, satisfying the height requirement, and it will also use a column spacing with sections of 32 feet with a central 16-foot span to maintain symmetry across the design. Shown in this image is the view from the east-west side of the 160-foot building. The 160-foot building will use 8 sections of 20-foot spans, and the 200-foot building will use 10 sections of 20-foot spans. The construction of this building will be a braced steel frame, as construction manufacturing is available locally, and the steel can be sourced from recycled materials, and at end of life can be easily be recycled as well. This slide shows a top-down view of the structure where you can see the 32 by 20 foot and 16 foot by 20 foot sections of the floor that will be made up of a 6-inch reinforced concrete slab and deck structure. These two images are the proposed architectural layout of the first floor on the left and the second floor on the right. The design requirements for the first floor are that it be made up mostly of departmental offices, lab space, and computer lab space. The second floor is to be made up primarily of large classrooms and medium-sized classrooms. And in the layout of this building, there is a stairwell and elevator for access on each floor on both of these levels for the 160-foot and 200-foot buildings, as well as a bathroom on each floor for each building. The architectural design of the third floor is similar to the second floor in that it is designed to be primarily made up of mostly large and medium-sized classrooms. And the fourth floor is required to be where faculty offices are located, as well as additional departmental office space and additional lab space. The requirements for the architectural layout were that there be 40 faculty offices, 4 large classrooms, 20 medium-sized classrooms, 7 labs/dean offices, and 6 computer labs. The proposed architectural layout shown here would include 44 faculty offices, 10 large classrooms, 28 medium-sized classrooms, an additional 4 small classrooms, 7 labs, and 6 computer labs, while maintaining or exceeding the required square footage requirements for these facilities. To begin the structural analysis, the loads applied to the building have to be generated and distributed onto the structural framework of the building. The loads applied to the structure will come from the standard loads defined by the American Society of Civil Engineers in the ASC 716 design guidelines. A sample of the loads are shown in the table on the right based on standard construction items that the building will include. Note that for the purpose of this project, the wind load on the building has been simplified to a uniform 10 psf. However, given the limited height and location of this building, this still should be an accurate representation. Also, other loads such as lateral forces from earthquakes have not been considered due to the geographical location of the building. As part of the load and resistance factor design, The following 11 load combinations, as defined by ASCE 716, will be included in the analysis for the factored load design. To aid in the structural design of the building, the Structural Analysis Program SAP 2000 will be used to generate the design loads for each individual member. The image on the right shows the 160-foot-long building as it is modeled in SAP 2000. After the standard loads have been applied to the model in SAP 2000, along with the standard load cases, the design loads in each individual member are calculated, and they have been grouped together in the table shown below, where similar groups of loads have been grouped to similar members to generate factored loads for the 20-foot beam, the 32-foot beam, the 16-foot beam, an internal column, an external column, and a roof truss and bracing member. To design individual structural sections, the design process used follows the American Institute of Steel Construction's Steel Design Manual, where the beams and columns were selected from available W shapes. Some assumptions that were made in the design of these members is that the beams used in the floors of the structure will be assumed to be continuously braced by the concrete slab that sits above them, and that the columns will be braced along their minor axis by the interior and exterior walls that surround them. Also, the surface ability limit state defined in ASCE 7 for deflection will use L over 240, as the ceiling in this design will not be susceptible to cracking. For the design of beam members, the factored design loads can be compared to the bending moment capacity and shear capacity from Section 3, Table 3.2 of the AISC Steel Construction Manual, as the beams are continuously braced. Once an appropriate section has been selected, it is checked for compactness, assuming an A992 steel is to be used for these wide flange members. The last limit state that needs to be checked for beams is a serviceability limit state defined by deflections due to live loads. The deflection limit state is assumed to be generated from an approximately evenly distributed load based on the tributary area from the concrete slab, and will be compared to the AIASCE 716 requirement of L over 240. For compression members, the most important limit state to be evaluated is the buckling limit state. For any section that's not continuously braced, the effective length of this structural member has to be calculated, then used to find the available strength shown in the AISC Construction Manual design tables for compression members. Lateral torsional buckling will not have to be considered for members that are continuously braced, such as the main column sections of the buildings. And lastly, the local buckling limit state of these sections is checked to complete the design of compression members. One limitation of the design of these individual members is that for the purpose of this project, steel connections such as the design of bolts and plates is not to be included in this design overview. So for the design of tension members, for roof trusses and bracing members, limit states such as block shear have not been considered, but have been instead designed for the basic tension limit states and also as compression members. For both buildings, 7 structural members have been designed for their corresponding load shown in the table. The linear density and the number of each member that will be required in the construction of the 2 buildings is then used to calculate the weight of steel that would be required for the construction of the buildings. Assuming an additional 10% of weight is included for steel connections, a total of 983,000 pounds of steel will be required. If the price of steel can fluctuate depending on many different factors, but has assumed to be around $4 per pound for a cost of $3.9 million for material.
Hi, my name is Ryan Isley, and I'm the head of hydrology for the Shaw Lane Power Plant Addition project for the Spartan Builders. As many students and faculty know, the Red Cedar River is prone to flooding the majority of MSU's campus. This construction project aims to reduce the impact of the Shaw Lane Power Plant addition on the surrounding watershed, which can be done by incorporating low-impact designs to reduce the building's hydrological footprint and by creating a stormwater network analysis to determine any areas that may be lacking. The first analysis for the site was for the existing stormwater sewer infrastructure. The design that has been decided on incorporates the use of the existing infrastructure and new proposed piping. There are two sections of the existing network that needed replacement that were near the football stadium parking lot. The replacement was due to the fact that they flowed the opposite way than the other connecting pipes. All other proposed pipes collect the stormwater from the Shaw Lane Power Plant area and deposit it into the proposed retention pond for sedimentation. The next assessment to be done for the stormwater network analysis was to create an AutoCAD surface. This surface was created to do a qualitative analysis on flow directions on the site, which was created to use the raindrop analysis tool, which was used to determine appropriate locations for proposed catch inlets. Surface contours were given in the MSU base map that were used to create a rough terrain for the existing conditions. The AutoCAD surface also made it extremely easy to access elevations anywhere on the site. With the information gained by the AutoCAD surface, the entire site area could be divided into catchment areas. These catchment areas were separated by surface types. The four types were roof, soil, pond, and asphalt, which all had different runoff coefficients, and boundaries such as curbs, existing inlets, and high points, and etc. After this was completed, a pipe sizing analysis was done for the new and existing pipes. First, the flow rate for each catchment was determined by using the rational method. The time of concentration was calculated using the noted formula, but as stated by the Ingham County Drain Commissioner, a time of concentration of 15 minutes can be used for construction areas under 10 acres. The use of this also makes the rainfall intensity constant for the rational method. Once the flow rate was determined, the radius of the desired pipe could be determined by rearranging the Manning's equation. After this, the velocity was checked to be under 8 feet per second as required by the Drain Commissioner. All existing pipes were found to match or exceed their required pipe size, and all new pipes were sized appropriately. The next part of the design is the retention pond. The retention pond is located south of the proposed addition and north of Shaw Lane. It collects incoming stormwater and allows suspended sediments inside of the stormwater along with the contaminants to settle and accumulate at the bottom. The requirements for the retention pond are that it's wedge-shaped, which means that it's narrow at the inlet and gradually gets wider towards the outlet. The inflow and the outflow are located on the opposite sides. It must have 4-to-1 side slopes, and there must be a 4-foot vegetative underwater shelf. Next on the list was sizing the pond. The area and the perimeter of the pond were determined by using the AutoCAD features. The required volume for the pond is the 10% of the 100 years storage, which is calculated by the following equation: 4,540 times the runoff coefficients and the multiplied by the total site drainage area. The 4-foot vegetative shelf, as required and as mentioned before, was included in the volume computations, and the pond's depth was determined to be 10 feet, which was not including the shelf, so it's 11 feet total. And the total volume of the pond is 79,484 cubic feet. The retention pond's inflow and outflow must also be designed to meet the requirements of the drain commissioner. The inflow is a 24-inch concrete pipe with a V-shaped mouth with ripraps going towards the pond to provide additional sedimentation. The outflow is on the opposite side of the pond, opposite of the inlet, and it is a riser structure which maintains the pond water level, and that is a 24-inch outflow storm sewer that flows into the bioswale. The next part of the design is the bioswale. The bioswale collects the overflow of water from the retention pond in events such as spring snow melts and large storms. It also provides additional filtering to stormwater coming from the surrounding catchments and the pond. The bioswale is a greener alternative rather than using traditional underground concrete stormwater piping. Additional requirements for the bioswale are having riprap at its inlets, a raised catchment to promote natural filtering through soils and vegetation, and a connection from the storm drain to the existing stormwater network. The final part of the design is the rain garden. The purpose for the rain garden is to reduce ponding in the catchment areas that were not collected for the retention pond. The purpose for the rain garden is to provide additional attenuation and sedimentation for this incoming stormwater. The rain garden utilizes natural filtration by native species. Permits for construction are as follows. The SESC, or Soil Erosion and Sedimentation Control Plan, basically states that silt fence will be surrounding the site to eliminate the escape of bare soil during construction. It also states that sediment is not going to be distributed into roads or bodies of water to be transported elsewhere. The NPDES is basically an agreement that the discharge of pollutants and toxins will be controlled. Each of these will have inspectors to verify that all requirements are being met and to notify the owners of any discrepancies.
Hello, my name is Yiru Bao, one of the two environmental specialists in the group. Today, I will be talking about current environmental design progress of SUMO model and SARS-CoV-2. This year, the focus on the environmental discipline specialists is to write a technical report summarizing all pertinent information relating to SARS-CoV-2 in wastewater treatment plants. Our goal is to find out all decay rates of SARS-CoV-2 and simulate a model of the decay rates of the virus in a plant performance review. The SARS-CoV-2 is activated in sewer systems because of the influence from infected people in urban areas. Therefore, different network nodes are analyzed and monitored. The lifespans of COVID-19 shows the virus in sewage and solid feces would be longest living within 3 to 4 days, which means the wastewater system needs to be paid most attention. By the relative research, SARS-CoV-2 in sewer system is negatively affected by elevated temperatures by comparing the time charts from SUMO model. SUMO model could be a good fit between results based on the performance of modeling and real data, which concludes that the model is promising and might be used as a support for the design and development of efficient operational conditions for wastewater treatment. It is also being used to model the individual wastewater processes that were assigned. This will allow the team to more easily visualize each piece in order to determine which perimeters are most susceptible to the virus and where to best detect and remove it. IFA's integrated fixed film, activated sludge, and MBBR moving bed biofilm reactor are analyzed and researched by both of the group members. Here are the 4 time charts presented by the sumo model. As you can see, the upper 2 charts represents the IFA's reactor, and the lower 2 charts represents MBBR reactor. From the default scenario, we could set temperature as 15 degrees Celsius. Because of that, the virus inactivation rate was set as 0.114 per day, and the virus influence was set as 100 GC per milliliter. And the stop time was set as 100 days, and the data interval was set as 1 hour. After setting those parameters, we clicked Start, and the time chart will be operated by the sumo model. The red line represents the virus effluent, and the blue line represents the virus effluent. And you can see the data for the virus effluent. That maximum concentration is 3.4 GC per milliliter, average concentration is 2.0 GC per milliliter, and minimum concentration is 0.51 GC per milliliter. Two time charts with 2 different temperatures and decay rates were compared in 2 reactors in 100 days. The influence of virus was set as 100 GC per milliliter, and the influence of virus was close to 0 GC per milliliter. Through the process, the decay rate 0.114 in 15 degrees Celsius and the decay rate 0.28 in 37 degrees Celsius was input to the scenario by the reference of decay rate table. 2 time charts will still appear nuanced between averages. For IFAs, the average of virus concentration fell from 2.0 GC per milliliter to 1.2 GC per milliliter with increasing temperature. In MBBR, the average declined from 3.1 GC per milliliter to 2.5 GC per milliliter with the elevated temperature. Therefore, comparing 2 different reactors, the IFAs could more efficiently inactivate virus than MBBR from the above results. Through comparison and discussion, the IFAs could be more efficient and well-rounded on dealing with the SARS-CoV-2, and the temperature becomes the most important parameter of the virus inactivation.
Hello, this is Sam Malatesta, one of the 2 environmental specialists in the group. While the main task of our project was to research the SARS-CoV-2 virus decay and model it using SUMO, we were also tasked with achieving LEED certification for our building. The LEED certification program is a point-based system designed to evaluate the sustainability of newly created buildings. Depending on the number of points earned, different levels of certification are reached. Basic certification comes at 40 points, with 50 points silver is earned, 60 points earns gold, and 80 or more points earns the platinum rating. There are a variety of different categories to earn points in, with different requirements for each, and information on how each point is obtained is laid out in the LEED credit library. The points required to achieve LEED certification for our structure can be broken down into 3 main categories. Since the build's location is predetermined, the building would automatically gain points for its proximity to required facilities, schools and hospitals, as well as its aim to reduce miles driven. Additionally, it will be built in an area with other facilities present, and it will be built along the newly created bike path and along the bus routes. This location group alone nets us over half of the points we need to achieve the basic LEED certification. Making use of efficiency upgrades is another easy way to gain points. Using energy efficient lights, heating, and other products can gain up to 18 points alone. Use of renewable energies generated from the source, in our case we'll be using rooftop solar, will net all 5 of the possible points. The use of water-saving toilets, sinks, and showers whenever possible, as well as the use of water metering, will also help cut down on water use. Limiting environmental impacts can be best achieved by modeling our structure after natural systems. This will allow us to reduce runoff by 70 to 90%, netting us 1 to 3 points, depending. Additionally, reducing light pollution by avoiding needless light sources and installing 2 level 2 chargers on at least 2 spots to meet the electric vehicle requirements will help net more points. Finally, life cycle impact reduction and erosion control plans will be created before the project's construction to minimize construction pollution. With the points laid out here, I believe that our team will achieve the highest LEED rating of Platinum. Understanding PCBs and their history in this site is another key piece to this project. PCBs, or polychlorinated biphenyls, are man-made organic chemicals known as chlorinated hydrocarbons. There are many forms of PCBs which range in their toxicity to human health. However, none of them degrade naturally in the environment. Due to this, manufacturing of these products was banned in the US in 1979 by the EPA. PCBs generally appear as oily substances and were commonly used in transformers and capacitors at power plants, as well as motor oil, cable insulation, plastics, and floor finishes. Sites that contain this hazardous material are designated Superfund sites and must eventually be cleaned up. Before it was chosen as the location for the new build, the area was home to the Shaw Lane power plant. After its destruction in the late 1900s, oil-soaked soil was noticed around a concrete pad previously used to anchor the plant's transformer. Sampling conducted by the Swanson Environmental Inc. revealed that PCB contamination persisted despite removal of these oily soils. This resulted in over 100 hand-augered soil borings to be taken and groundwater in the area to be tested. The analysis revealed 2 primary areas consistent with the locations of the dielectric fluid containers on the old site. These 2 sources had PCB levels above 50 ppm, with the goal to achieve 1 ppm. And even this 1 ppm threshold was surpassed 50 to 75 feet from the main sources. Fortunately, no PCBs were detected in the groundwater in the area. And finally, in 2005, MSU received several bids, eventually choosing Pitch Company to clean up the area. Since then, the area has been cleaned and remediated, and there should be no more issue of PCBs in the area for the future build.
Now that you've seen all of the proposed designs for the project by our specialist, I will move on to discuss project construction costs. The new proposed building was designed with a 104,000 square foot blueprint with an estimated cost of $4,493,000. This cost includes material, construction, and design fees. It excludes any internal architectural furnishings or finishes. The proposed drainage system was estimated to be $264,000 for excavation, construction, and installation. The new transportation design construction cost was estimated to be $171,000, and the new proposed pavement design construction cost was estimated to be $112,000. In total, the overall estimated project construction cost is $5,050,000. Based on the knowledge of limited construction during MSU's fall and spring academic calendar, along with the off-season construction months in the winter, the estimated project construction timeline is 3 years in total for completion. Lastly, we have our closing remarks. Spartan Builders wishes to extend our gratitude to the faculty of the Civil and Environmental Engineering Department and the professional advisors who have volunteered their time to contribute to our project. This design was a challenging yet rewarding learning experience that we will remember for years to come. Lastly, we would like to give a special thanks to Mr. Anthony Engel of Michigan State University for providing guidance for us through this course. We hope you enjoyed this presentation. Thank you.